So good afternoon, everyone, and welcome to our next hybrid colloquium. I hear a bit of a Zoom feedback here. So welcome those of you here in McLennan Physics 102, and those of you online as well. It's my great pleasure to introduce today Tiffany Shaw, Professor Tiffany Shaw from the University of Chicago. Tiffany is a physicist, an atmospheric physicist, who has been at Chicago for several years. Prior to that, she was an assistant professor at Columbia University. And prior to that, a postdoc, and then prior to that, a graduate of our program in 2009. She got her PhD here with Ted Shepard in 2009, and it's a great pleasure to have you back, Tiffany, after many years, probably too long for a colloquium. Tiffany has been doing fantastic work in the area of theoretical atmospheric and climate physics. As we'll hear today, she brings a model hierarchy perspective, which is really important in our field. But in terms of fundamental contributions and our understanding, her work has really given great insight into the nature of heat transport in the atmosphere, the sensitivity of the storms and storm tracks and storm statistics to global warming, monsoonal circulations, many areas, including present day climate and past climates as well. It's just a great pleasure to have her here. She's a recipient of several early career scientist awards, including the Holton Award from the AGU and the McElwain Award as well. Today she'll be telling us about closing the gap between simulation and understanding climate change. And I'm very pleased to welcome her. So let's give her.
Hey. Okay, I'm going to take my mask off and stand behind the red line. So thank you, Paul, for that kind introduction. It's really a pleasure to be back and to see familiar faces and also see the new faces, the new generation. So I'm going to be talking today about closing the gap between simulating and understanding climate change. Before I get started, if I can get started, my slide is not advancing anymore. Oh yeah, there we go. Okay, I'll stand away from here. Okay, to acknowledge contributions from two former postdoctoral fellows in my group, Dr. Eiko Voigt, who's now a professor at the University of Vienna, and Dr. Jihong Tan, who's now an associate research scientist at Princeton University. You cannot hear me. Okay, that's better. Thank you. Okay, now this is not working again. Is there some radio? Okay. Okay, working now. So today's talk is going to be about Earth's climate. So I figured I should give a little bit of background. So we know Earth's climate today very well from the wealth of observations we have, including from satellite data sets. Shown here is an image from a NASA satellite. And so the question today is sort of what are the broad climate patterns that we're used to, the climate patterns that make the Earth habitable, that sustain our agriculture, among other societal endeavors. And so as a physicist, I'm going to simplify this complex atmosphere-ocean system and give you the sort of basic picture of Earth's climate as we move from the tropics here at the center toward the pole. So we have the wet and warm region at the equator. This is where most of the rain falls. And as we move poleward in both hemispheres, the climate changes. It changes to one that's dry, where evaporation exceeds precipitation, and where the winds are westward. So from, for example, Europe toward the Americas, which enabled early navigation. As we move poleward again, the climate changes once again to a region that's wet, where precipitation exceeds evaporation, and the wind change sign to eastward, where we have these storm systems that are moving along with the jet stream. And then finally over the poles, not shown in the schematic, of course it's cold and there's ice and snow. So this is what we're sort of used to, and one of the most important questions in climate science today is how are these patterns changing, not only in latitude, but longitude in time, but also into the future. Well, if you go on Google and you search, climate of the late end of century, 2080 to 2099, you'll find images like this. So on the left, what's being shown is the Earth's temperature relative today in 2090. And so the warmest temperatures are in purple. The basic patterns here are suggesting warming over land, significant amount of warming over land, particularly over the Arctic. And then when we look at the right-hand side diagram, again, this is a simplified schematic, and what it's illustrating is the expectation of the future will be that these climate zones will shift poleward. Okay, the red arrow indicates that, and this has huge implications if you think about where the storms are going, the rain that they carry with them, extreme events that they're associated with, the agriculture that we rely on, where the rain falls. So this is a really important question. So how do we know this? How do we know this? And of course, the answer is that everything that we know about the future doesn't come from observations, obviously. It comes from some prediction or some model that is forecasting the future given a specific pathway of carbon dioxide emissions, which is what underlies anthropogenic climate change. And so the climate model simulations, which are giving us this future prediction, are really important, and not unlike the predictions of weather, of course, but on very different timescales. So there's two important things about these climate models that we need to understand. One is that they are built on the laws of physics. We have the Newtonian mechanics of atmosphere, ocean, fluid dynamics, which represents then partial differential equations, nonlinear partial differential equations of conservation of mass, momentum, energy, water, chemical constituents. But these are not equations we can solve by hand, and so we need to solve them numerically. And so that introduces the following schematic where we have discretized the Earth's surface into this horizontal and vertical grid where we find the solution at these grid points. But this then introduces the second part of the climate models. This discretization is finite, and so there's physics that's encapsulated or that exists on length and time scales that lives within these boxes, what we call subgrid scale physics. And that includes important things like clouds, the interaction of electromagnetic wave radiation with clouds, with the atmospheric gases. And that's quite uncertain. So how we represent physics on smaller length and time scales, given only information from the numerical simulation on these grid boxes, is a form of a closure problem. So I want to take away from this, this diagram is that there's two components to these models. There's the laws of physics that are fundamentally at the core, and then there's these representation of small grid scale processes, subgrid scale processes that are inherently uncertain because we're trying to represent complicated physics on this very coarse domain. And that will introduce structural uncertainty. We don't necessarily know the equations for these physics given the grid scale, and also parameter uncertainty because we don't know all of the aspects of convection and all the parameters that we might want to know in order to close the subgrid scale equation. And so that's what ultimately, leads us to the following issue that, well, we can take these models and we can integrate them in time to get a prediction of the future climate, which is the simulation part. We don't necessarily know what physics, whether it's the physics or the structural and parameter uncertainty is underlying that response. And so that's just saying that simulation does not equal understanding, something that was coined by Isaac Held in a seminal paper that he wrote in 2005. And so the idea then is for any given emergent response, like warming over the continents that we saw in that projection that we looked at from Google, is it the case that that emerges from the equations themselves that we can understand, or is it somehow tied to this physics, that subgrid scale that has structural and parameter uncertainty associated with it that we're not confident in? And we need to distinguish these two if we're going to have policymakers or the public take these forecasts seriously, okay? And so this is a duality that's been articulated in the 21st century on Twitter, by Jeff Vallis, who is someone who essentially wrote the textbook of the Newtonian mechanics applied to fluid dynamics that underlies these models. And he argues the following, that he wishes we could hold these two perspectives at the same time. That one, we have these powerful numerical models that can tell us what Earth's future climate looks like, and we should not only say that they're invaluable. Here he calls them GCMs, or general circulation models, but they're really great advance. And why they deserve love and respect is because they made predictions that have subsequently been seen in observations, and that's the gold standard in physics. Okay, but on the other hand, we need to be mindful of not always just trusting them blindly, because they have this uncertain component that could underlie the response and therefore isn't trustworthy until we have a mechanistic understanding to accompany the simulation. And so it was only 2 days before, or 3 days later, the 2nd of October, that the Nobel Prize of Physics was announced for 2021, and it was given to 3 scientists studying complex systems, but 2 of them are climate scientists. Syukuro Manabe and Clausius-Clapeyron for the physical modeling of Earth's climate, quantifying variability, and reliably predicting global warming. And the main aspect here is that the claim that these 2 scientists are able to hold this duality and sort of work within the confines of the model. No model is perfect, but all models are useful, and also extract physical understanding amongst the complexity. And so that really frames the talk today. So we're going to acknowledge the gap between taking state-of-the-art models on the one hand and using them and loving them and making a prediction of the future, but understanding that underlying these models, while we have the physics, we also have the uncertainty. And so we need to bridge the gap between not only simulating the climate, but understanding what patterns are emerging from these simulations and why. And so what the talk is going to do is give you the path forward. How are we doing this as climate scientists, as physicists who study climate? And the 2 examples will be first from that Nobel Prize winning research for studying Earth's climate, the work of Syukuro Manabe and colleagues, that focus mostly on the temperature response, as I'll show. And then we'll turn to more recent work from my own group, where we have been focused specifically on that poleward shift and what physics underlies that shift. So let's start way back in 1967, when we had basically the goal of Manabe and colleagues at this point was to predict the temperature response to a CO2 increase as a function of height. So given the computational resource at the time, that was a reasonable target, and it was building off of research that had already looked into this a little bit, and certainly had known already that there was warming in response to CO2. But what's beautiful about some of these early papers is that they provided schematics of the model. And so what I'm going to do here is to show you how this model blended these 2 pieces that I've outlined. So let's highlight first the components of the model that are based on the laws of physics, okay, that we understand. The model was integrating an equation for temperature because it wanted to find out what the temperature was as a function. This was really the global mean temperature, only height dependent at that point. And this is the first law of thermodynamics for an ideal gas. The first law of thermodynamics is the internal energy, and that depends on temperature. So that's what that represents. And then also we're taking into account water vapor and its dependence on temperature through this analytic relationship of the water vapor mixing ratio and temperature. And so then what had to be combined with these 2 ingredients was the physics of the model that represented convection and radiation. And so these 2 were not resolved in the model, in the sense we weren't representing cumulus clouds. And so I'm going to color code those in red, because what Manabe and colleagues were doing was representing this physics in a simplified way. And in particular, the physics of convection and its vertical heat transport was represented as a relaxation of temperature as a function of height. And then when they needed to compute the temperature change due to radiation, they had to make assumptions about things that we know well, like the atmospheric composition of gases, including carbon dioxide, but then also what type of clouds are in this column of atmosphere? What are the cloud properties? Are they high, low, mid-level clouds? Do they reflect radiation? Do they absorb it? And so this is where all the structural and parameter uncertainty comes in, where you could make different choices and potentially get a different answer. So what Manabe and colleagues did was they combined these two pieces. They made some assumptions about the parameters and they integrated the model forward in time. And they made the first prediction, or one of the first predictions, of the temperature response on the x-axis as a function of altitude for 3 different carbon dioxide values, going from 150 parts per million to a pre-industrial value of 300 to some future concentration of 600. And today we're about at 400. And so amongst all of this complexity emerged a very simple temperature response. In the upper layers of the atmosphere, the so-called stratosphere, we see a cooling. And in the lower layers of the atmosphere, in the so-called troposphere, we see a warming. And the beauty of this model was that we could understand in the upper atmosphere, this was a consequence of radiation. The loss due to energy due to radiation exceeded the gain from below. And in the lower layers of the atmosphere, we understand, well, this is now a consequence of the greenhouse effect and the increase of the opacity of the Earth's atmosphere and the changing temperature that is a consequence of that. But they did more than that. They didn't just simulate this response. They also went into the model to try to understand what factors controlled the model temperature warming at the surface. So here is the table in the model where they focus specific on the doubling of CO2 from 300 to 600 parts per million by volume. And they showed that for this average assumption of cloudiness, it was 2.36 degrees. In this case of fixed relative humidity. And what that means is that the humidity is allowed to increase proportional to its dependence on temperature. And then they did another case with the same model where they removed the clouds from this atmospheric column. And this is a clear sky. And they found that there was even more warming, 2.92 Kelvin, than when they had the clouds in there, which suggests in this model, the clouds are negative feedback, partly due to their role as changing the Earth's albedo. So that helped them understand how clouds were impacting the surface warming, how that structural uncertainty of the parameter choices they made impacted the model simulation. And then finally, they could consider the case of fixed absolute humidity. So if they held the water vapor content of the atmosphere fixed, what would happen to the surface temperature response? And so here you can clearly see that it's much less if the water vapors are not allowed to change. And this is now something we refer to as the water vapor feedback. So water vapor is a powerful greenhouse gas. And so if you allow it to respond to the temperature increase, it amplifies that temperature response through a positive feedback. And so we've learned all of this, which subsequently is continues to be true in all of our models, from a very simple one-dimensional calculation, temperature as a function of height. So fast forward 10 years later, computational power has increased, and they now consider a model that is a hemisphere, half land, half ocean, and they upgrade the physics of the model in addition. So here is the diagram where we can outline the different core physical aspects of conservation laws. The first law for thermodynamics. We now introduce the movement of the atmosphere. That's conservation of momentum. So this is Newton's second law. We have conservation of water and the energy balance at the surface. So that's the one hand. And then on the other hand, of course, we identify these structural and parameter uncertainties, the cloud type, the cloud amount, latent heat release, the hydrology of the surface. And here we also have something new added to the model in terms of physics, the role of snow and ice in affecting the Earth's surface albedo, which is to say how much sunlight is reflected from the surface. And obviously snow and ice are quite reflective. So that's all put together and integrated forward. And what they showed in 1975 is how this affected the prediction of temperature when you take the doubling of carbon dioxide minus the standard concentration as a function of latitude and altitude. And so what's clear is that adding all this new physics, and there was quite a lot added, doesn't really change what's going on up in the stratosphere. What fundamentally controls that response is just radiation. Okay, radiative cooling, radiative loss of energy. Something very important emerges in the troposphere. The warming is not uniformly distributed as a function of latitude. It's warming everywhere, but at the surface, there's more warming over the pole than at the equator. And the model, they could go into the model and understand that this was a consequence of adding the physics and the albedo surface effects of ice and snow. You have ice and snow, and you warm the surface, you melt it. And when you melt it, you reveal a surface that's darker, which allows more sunlight to be absorbed, which allows more warming of the surface, which allows more melting of the ice. And this is what we now refer to as the snow and ice albedo feedback. But conversely, in the lower latitudes of the equator, the warming is amplified aloft, quite a distinct pattern from what's happening over the pole. And this actually is something that emerges because of the combination of radiation and convection. It could even have been seen in 1967 if they looked at differences rather than absolute temperature. Here we're looking at a temperature difference. And so what's responsible for the warming aloft is that convection is transferring the additional warming and latent, and the water vapor holding capacity at the surface has increased, and the convection transfers that air aloft, and the latent heat is released aloft, which leads to the warming aloft. So this is a signature of convection and its heat transport. So we can identify in each case where the physics is contributing to this warming response. And then finally, by 1989, there's no more diagram of the model. At some point, the model gets so complex, you don't create a diagram anymore. It's too many boxes. But what's being added here is the role of the ocean and the movement of the ocean circulation. And also realistic geography. Now you can actually see the continents and how coarsely they're being resolved, but they're there. And the computation was to look at the time dependence of the surface temperature response as we increase the CO2 1% per year as a function of latitude and longitude. And what's amazing is that the temperature pattern in the northern hemisphere hasn't really changed that much. Where you get the maximum amount of warming is still over the pole, even though you've added in, again, more and more physics. But what has changed quite clearly is in the southern hemisphere, we're getting regions where there's actually cooling. And these so-called warming holes were understood in this model to be a consequence of the ocean taking up the heat and moving it down into the deep ocean in a transient way, which eventually, obviously, the whole ocean will heat up and this will go away. But this was a signature of the ocean physics operating on transient timescales. And so what I really want to do then is frame this example and how it was a powerful, to shed the light on how we could move forward in closing this gap. And I think what the real takeaway here is the power of using models across a hierarchy of physical complexity. As you increase the physics contained in the model, you can understand what emergent responses are tied to that physics. So starting in 1967, the cooling versus warming could be understood quite clearly to be related to the role of radiation and convection in driving these patterns. But even within this model, they went in and understood the role of water vapor. They could just have fixed water vapor or allow it to change. And it was quite clear that water vapor was an important contributor to the warming. And then, of course, the clouds. They could go into that model. It was simple enough, and they could understand if they removed the clouds altogether that the warming response wouldn't go away. It just would be, it would be slightly weaker because of this negative feedback. But then as they moved forward in complexity, adding snow, adding the movement of the atmosphere, the pattern of the stratosphere stayed the same, and the pattern in the lower atmosphere could be traced to this new physics of ice and snow. And then going further, as we continued to have the ice and snow, that pattern stayed, and what would emerge is the physics associated with the ocean circulation in these warming holes. So that's really going to be the first example. If you want to understand the complexity of the full problem, it's a good idea to try to break it down and trace through some signal that emerges and try to understand its physics. Is its physics associated with something we understand well? That's due to do some underlying physical relationships, or is it to do with clouds or things that we're uncertain about? And this was a clear path how we could do that. So what we're going to do now is tackle a different problem. Okay, go back to this diagram and say, oh yeah, Manabe really showed us the way here for temperature, but what about this signal here that I argued was really important if you start to shift these climate zones in latitude, in particular poleward? It's going to have really important implications. What underlies this, and can we understand the physics of it? So let's first motivate that this is a very robust signal across these complex models. So circa 2007, we have 15 models, okay, that perform these scenarios of the prediction of how the climate will respond to increasing carbon dioxide concentrations. And we have three different ways of quantifying that temporal dependence of carbon dioxide. So each model is labeled with a number, and this is late end of century minus the present day. And what you're seeing on the x-axis is the shift of that position where we changed the sign of the wind from westward to eastward. And so it's telling us here in the northern hemisphere, you're shifting toward the pole, that's red. And in the southern hemisphere, you're shifting toward the pole, that's blue, but it's southern hemisphere, so it's negative, toward the south pole. And on the y-axis is the shift of the dry zone, where we change sign from dry to wet. That boundary is also shifting poleward, that's the y-axis. But there's nothing implied about the physics or the mechanism connecting them. It's just a simulation. This is what the simulations are telling us. Similarly, as we move into the region of the jet stream and the storm tracks in mid-latitudes, if we look at the position of this mid-latitude systems as we look into the future minus the present day across the southern hemisphere or the North Atlantic or the North Pacific, we see this tendency of a poleward shift across now many more models, almost 40 models, okay? But they all seem to be doing this, especially in the southern hemisphere. There's certainly some deviations in the northern hemisphere seasonality. So why? This is just what the simulation is telling us, not why it's happening. And so what we're going to do is bring to the table a few more tools. We will make use of Manabe's seminal work in a minute, but I want to start with taking a step back even further to thinking about the theory underlying this, the equations, the partial differential equations that tell us about how the winds, what they depend on, and how that might change with climate change. And the theory will really leverage the role of moisture, something that's been underappreciated, I think, for winds. So here is the theory, very simple. We're going to start with the so-called Clausius-Clapeyron relation. We have the saturation vapor pressure, so the moisture holding capacity of the air, the amount of moisture in kilograms per kilogram of dry air as a function of temperature. And this is just a phase curve. Okay, so if I take Earth's global mean surface temperature, 285 K, move up to the blue line, that's the maximum amount of water vapor the air can hold before it's going to condense. Okay, so it's like an upper limit. If I warm the climate by 4 Kelvin, I'm going to move to the right, the water vapor holding capacity of the air increases. And I can say quantitatively how much, by just linearizing the slope here and taking the climate change delta between the warmed climate minus the current climate of this QS star and weighting it by the present day. So it's a fractional increase. And this is the relation that's going to matter a lot in this talk. Alpha is 7% per Kelvin times the amount of warming you get. So 4 Kelvin times 7% is 28% increase for this thought experiment. That's huge. And it was recognized that this has really important implications for this wet and dry patterns that we see on Earth today. In a seminal paper by Held and Soden, they made some very elegant arguments using the conservation of water vapor. Okay, so they argued, well, what really matters in the conservation of water vapor, which is what dictates precipitation minus evaporation, is moisture flux convergence divergence. So where moisture flux is converging to a point, precipitation exceeds evaporation and it's wet. And where moisture flux divergence occurs, you have evaporation exceed precipitation and it's dry. So if you assume that this water vapor transport or water vapor moisture flux convergence is constrained by the Clausius-Clapeyron relation, you can make the following prediction about how this hydrological cycle will respond to climate change. So the climate change delta of precipitation minus evaporation they showed could be related to the Clausius-Clapeyron sensitivity times the present day patterns of precipitation minus evaporation. So this is quite profound. It means that if you're in a region today where precipitation exceeds evaporation, then the right-hand side is positive definite and the left-hand side is positive definite, which means wet regions today will get wetter under climate change. And conversely, if you're in a region today where evaporation exceeds precipitation, which means it's a dry region, the right-hand side is negative definite, and the right-hand side is negative definite, left-hand side is negative definite. So dry regions get drier. So they basically combine this constraint with the conservation of water vapor to deduce a leading order expectation of how the hydrological cycle will respond. Even more importantly, they showed this is what the models predict. And even more importantly, we're beginning to see this in observations. And it will continue to emerge as we evolve into the future. So let's leverage this success, but turning our attention instead to winds and not the pattern of wet and dry, but to the east-west pattern we talked about before. So the first thing you learn about winds when you take a class in geophysical fluid dynamics, which is the physics underlying fluids on in a rotating stratified on the rotating stratified Earth that we deal with for climate, is that circulation doesn't depend on the global mean temperature. It depends on temperature gradients, in particular on latitude gradients, focus of what I'll take today. And so let's revisit this constraint that we argued was so valuable for the hydrological cycle, but focus on not the global mean temperature, but the temperature difference between the equator and the pole. So here's a temperature of the pole, 260, and a temperature of the equator. It's a huge gradient today. And now we're gonna go into the future, warm this planet by 4 Kelvin, and what we can clearly identify is that this moisture gradient will get steeper. It will become even larger in the future. And so intuitively, that's the case because it's 28% of the moisture you have to start with. So in the poles, it's really dry. So it's 28% of a small number. But in the tropics, the equator, it's 28% of a really much bigger number because it's moist there to begin with. So that's intuitively why this steepening happens. And that's also clearly a consequence of this nonlinear Clausius-Clapeyron relation. The question now is, what does this have to do with winds and how do we leverage this to understand the polar shift? Well, the next thing we have to bring to the table is the theories of what the winds depend on. And again, analytic equations representing our understanding of the underlying conservation laws, the physics that govern these wind patterns. This work by Carey Emanuel, which in the 90s we only had black and white diagrams, summarizes sort of this important work, where in the diagram the air is rising, where it's deep convection, we have rain, and it rises and it moves poleward, and it sinks in the region where we have low clouds and no precipitation. And there's this important gradient between where it's warm and moist and where it's less warm and moist. And so what he did was he took this energetics of the moist atmosphere and the momentum conservation of these wind systems, and he derived the following dependence of the wind. This is the wind in the east-west direction at the surface. It depends on the surface temperature minus the temperature of the tropopause, the boundary between the stratosphere and troposphere. The Coriolis parameter F, which depends on the Earth's rotation, A, the radius of the Earth, and then importantly here, this latitudinal gradient, partial derivative with respect to phi, latitude, of this S sub S, the subcloud moist entropy, relative to a critical value, which we don't need to worry too much about because the critical value is just what we need to exceed in order to get this overturning. If we don't exceed it, we just have a thermal equilibrium and no overturning in the atmosphere. So what you can show is the dominant thing that's going to matter for the climate change between the warm and the present day climate is really how this moist entropy gradient is changing. And why this is important is because it's moist entropy and it can be connected to the Clausius-Clapeyron relation. So if we follow through that dependence, the Clausius-Clapeyron sensitivity here again, alpha delta TS, 28% for 4 Kelvin warming, is outside, and then it's multiplied by the moisture gradient we have today. And so all this is saying is it's going to follow this expectation that when we warm the climate, the moisture gradient will become steeper, okay, between the equator and the pole. And once we know that, then it seeks, all we need to know then is to substitute back into the wind relationship and show that this whole thing is going to be negative definite, because this gradient between the equator and the pole is such that as we go toward the pole in the northern hemisphere, we will have less moisture as we increase phi. So this is negative. All these other things are positive definite, and it tells us that this wind response will be westward. What this means then is where we've changed sign of the wind from westward to eastward, we're adding a negative number, and that's shifting this nodal point of the wind poleward. So combining Clausius-Clapeyron with the theory for what the winds depend on in Earth's climate today, we can deduce that this wind response in the tropics will shift this boundary of the tropics indicated by the change in sign in the wind poleward. Now we can turn our attention to the middle latitudes where we have the storms and the jet stream. And here we have to shift gears because it's a different theory that's not the same as the tropics. What we have there is just a hemisphere of atmosphere that we need to account for all the energy transfers. And we'll just connect it to the storms as a consequence. And so it's an energy model where we just account for all of the different sources and sinks. And we have the first in the vertical, the radiation, which is the combination of all the sunlight and the earth light for both the surface here and the top of atmosphere. Those are all taken together in net sink. So the arrows are pointed outward, and there's not much of a difference between the equator and the pole. It's about 100 watts per meter squared for both regions. Whereas at the surface, there's a clear energy source coming from surface heat exchange due to evaporation and sensible heat flux. So this is conduction of temperature. This is evaporation of moisture at the surface. That's really large in the tropics because it's warm there, which allows for more exchange. And in the high latitudes, it's very small because we've got colder temperatures, but also capping the surface here with ice and snow. Now, more energy is going in the tropical regions than is being lost, and more energy is being lost than being gained here. So neither region is in equilibrium. And so we can deduce the existence of a third form of energy transfer. This is now a horizontal arrow indicating what we call advection, the movement of the atmosphere that brings warm and moist air poleward and dry and cold air equatorward. And this is where the storms play a leading order role in regulating this equator to pole imbalance. And we can think of the position of these storms as a nodal point again between the region where we're diverging energy from the tropics to the region where we're converging energy in the high latitudes. So it's where it changes sign. That's the position we're going to track. But why this is important is because this theory connects to moisture. And previous theories don't, so they can't allow us to leverage what is the connection to the Clausius-Clapeyron relation. So here's the fractional change of evaporation, which was one of these surface heat exchange blue arrows. It has been shown in the literature to be bounded in an upper bound sense by the Clausius-Clapeyron relation. And so once again, from our diagram, we should expect that the evaporation gradient between the equator and the pole should increase, just as we saw for the saturation specific humidity and subcloud moist entropy in the previous example. And so as we go to modify our diagram, we globally warm, the blue arrows get longer, but again, 28% longer of the length they started with. So there's more of a lengthening here than in the tropics. We enhance the gradient between the equator and the pole. The black arrow has to compensate, assuming that the radiation isn't changing its equator to pole gradient, which is the assumption we make here. This also has a consequence for the shift, as we'll see. So we can articulate that mathematically as just the conservation of energy flux divergences. So the atmospheric energy transport by the storms is balancing this increase of atmospheric energy flux divergence by the evaporation gradient increase, which is again related to Clausius-Clapeyron, which is adding a positive number to the nodal point where we've changed sign from divergence to convergence, shifting that poleward. Okay, so in both cases, what we've been able to do is say, well, starting with our knowledge of the connection between moisture and temperature, and given what we know about the storms and the tropical circulation today, can we leverage that to show what we might expect physically? And so what I've shown you is we expect a poleward shift. I haven't told you by how much, but that's what we expect, not an equatorward shift, although you could reverse all the arguments I've given you and say that should be equatorward shift for cooling. So that's also interesting. But what are we going to do now? Well, we're pretty far away from having just theorized this and trying to understand what's going on in the simulation. So we got to take another step. So we've got a mechanism in mind now, some physical understanding that we think might explain the signal. So now what we want to go do is test it. Test it in this climate model hierarchy, but circa 2020 or 2019, where we've got a much more sophisticated set of models to consider. Particularly on this really complex end, it's like everything we can think of that's important for making the most accurate prediction. And then what we systematically do when we go in the opposite direction is to strip away the physics, just like Manabe did. You strip away the ocean moving, strip away the continents. This is an aquaplanet that has not even any movement of the ocean. It's just a slab, just a layer of water at the surface. And then we can strip away rotation and just get at that 1967 model where it's just radiation and convection, and there's not even any rotation. So the question, of course, is which model should we try to test our mechanism with? Well, we're going to use the aquaplanet because it combines the ingredients we need. We need water vapor, we need rotation, we need conservation of energy, and that's all included in this aquaplanet world. Another important aspect of the aquaplanet is that it can be easily traced back to this complex set of models that pretty much all predicted the polar shift. In particular, if you take the aquaplanet on its own and you increase the CO2 in that model, what happens is the tropical and mid-latitude circulations shift poleward, which is measured here on the y-axis. So even after stripping away all that complexity, we see the emergent signal, and it's outside the noise, which is indicated here by the gray. So now what we're going to do, because this is a simple enough model, we can go in and target the physics of what might be causing mechanistically the polar shift. And we can do things like the following to look at the response of the dry atmosphere, disable the ability of moisture to influence the circulation. So we just essentially hold it fixed as it is today, don't allow it to increase in response to the CO2 increase. And that's sort of like a null experiment. We expect there should be no polar shift if our mechanism is operating. And then we can look at three more things, which are the breakdown of which parts of the moist physics matters the most. So in magenta, this is our mechanism where we expect surface humidity induced by evaporation will introduce a change of the gradient and a sharpening of the gradient following Clausius-Clapeyron. So this is where we think the action should be if our mechanism is right. And then in the surface wind-induced evaporation is another way that we can influence moist physics, but that's not to do with our mechanism. It would be something to do with the wind response itself, sort of like a chicken and egg problem. And then finally, clouds. What is the role of clouds and how they interact with radiation in this model for instigating or shifting this circulation pattern poleward? So let's start with the null experiment where we don't allow the moist physics to respond. And what we see is that dry atmosphere response shows, basically no shift within the level of noise of this model indicated by gray. So it tells us moist physics is at the heart of this shift in this model. So now we have to figure out what part of the moist physics matters. So the next component was this and try to connect the poleward shift that they simulate to the physical mechanism that we've uncovered. And the way that we can do that is basically statistical, at least the way that I'm going to show that we do that here. So if we look at each individual model as a cross and how its tropical shift of the circulation is related to the surface evaporation contrast between the equator and the pole, which is essentially underlying that Clausius-Clapeyron model, because we can assume that those surface winds are not playing a role in evaporation, we see a good amount of variance explained, but not all of the variance is explained. And I think that's probably expected because of the role of the cloud radiative response that we found in the aquaplanet. But similarly, we can show the same for the mid-latitudes in the surface evaporation contrast. Again, teasing out the signal and a mechanism that explains it rather than just putting a bunch of X's on there where the X and Y axis don't have any physical meaningful relationship to each other, or at least not any clear mechanistic relationship. So that's the story for today. We began by highlighting the importance of using state-of-the-art climate models to make future predictions of Earth's climate, but needing to combine that with an understanding of the modeled responses to give the policymakers and the public reason to trust and have confidence in these future climate predictions. And we started by looking to Manabe and the pioneering work he did with his colleagues that won the Nobel Prize, where he illustrated for us two important things. One is to make use of a model hierarchy of physical complexity, but also to go into the models and target the physics that underlies them, test the sensitivity to clouds, test the role of water vapor. And so we basically followed that thread. We focused on the poleward shift, and we showed that if we combine the theory of water vapor and how it's connected to the circulation, we would expect a poleward shift. We then looked in idealized models to find evidence to support the connection between the poleward shift and moist physics by using certain null experiments and disabling the moist physics within that simplified setting. And then we bridged back to the state-of-the-art models by looking for relationships between the signal that emerges across these models and the mechanism that we uncovered using these other pieces of the puzzle to kind of create this holistic understanding. Of course, we'd love to have the observations in here too. That's really the next phase, and the poleward shift is beginning to emerge in the southern hemisphere. The one challenge with that is there's other signals that influence the wind patterns, including ozone depletion. And so we're eagerly trying to tease out these different signals and connect it back to the mechanisms we've uncovered using these other tools. But hopefully you get a sense that I've shown you a few examples of a few signals, but there's many, many other things that we're interested in, including extremes and so on. But we really need to lay the path forward to tackle these new questions, which is certainly the subject of future work. So thank you very much for your attention. I look forward to your questions.